Hello everyone. So here's only one people. So okay. So hello. Today I will talk about set. Set is like I think from my view is like the fundamental of mathematics. So I'll first introduce what a set is, and some relationship between different sets, and how to do the basic operations between sets, and in the last, I'll introduce one interesting topic, which is about the uh, infinite sequence of sets or the index of sets. But for now, you may not understand what is infinite sequence, but it's totally okay. So what is that? Set is just like a collection of objects, um, like a box of balls, and each ball you can call it an element, and it is the members of the set, which is the box. So that's very simple. And I think most of you have already learned set in high school already. So that's the same thing. That's the same thing. It's no obvious difference here. And if you want to say some element belongs to a set, like we first define A as a set and X belongs to a set, we just write this character. It's called a membership symbol. All right. But in some cases, set cannot always contain everything. And that's a theory based on the Russell's paradox, which I will talk about later, is that a set cannot contain everything in the universe. So there's must be at least one element that is not in the set. So if it's not in, just write this symbol to represent. So logically, X not belong to A. It's like it is not a case that X belong to A. So yeah, so that's the fundamental start. Okay, so and as you can see, sets can contain everything from numbers to like for example the Empire State Building can also be an element in the set. So sets themselves can also be element in other set. So we define element X belongs to set A, and A A is a set, but it can also be an element into set B, and B is an element into belongs to set C, and this can continue. It means X is an element of an element of an element of an element of possibly if we end here is an element of C, right? Okay. And I think the most basic relationship between different sets is set equivalence. How we define two sets are equal. Uh, if you still remember the logical operations, if and only if, then it's totally fine. So uh, if A and B, for example, A and B are two sets, if they are equal, then if and only if X belongs to A, then X belongs to B. So which means like every element, every member of A is a member of B. And if you check every member of B, you will find out it is an element in A. So that is the definition of equal. And if it's not the case, they're equal, we say, all right, we say it is not equal, which is here. So A is not equal to B. All right. So there's some basic ways of writing sets. If you here already understand what sets is, then I think if the elements are very small, the number of elements is small. We can also call it like the cardinality is very small. But yeah, cardinality is just like the number of elements in the set. So for example, for this set, AB negative pi root square 2 over 5. And this is a set of element of four elements. It's small, so we can write it out. Just use comma to separate each element and put a bracket outside, and that's done, right? And also uh, there's important uh there's important property of set, which is there's no additional property than the element in itself in the set. So what does this mean? It means that if you have um if you have 0, 1, then it's just 0, 1. There's no storage of information about orders or repetition. So 0, 1 is equal to 0, 0, 0, 1, 1, or 1, 0, 0, or you can say 0, 1 is equal to 1, 0 because the order is not stored in the set. So they're all equal. And if the elements, they're too much. Like if the set contains the integers from 0 to 1 million, then it's impossible to write each of the element out. You can write a trend, something like that. So that means from zero, probably 1 to all of the natural numbers. So that's a way to write a set. It's like a suggestion, but it's not complete. So this means the integer from 1 to n, but n probably is not defined. It's just mean okay, some number in the list, but it's finite. It's not infinite. And we can also define, like the most common situation to define set is defined with a property. So we can say A equal to some set, the set bracket set up, and element inside, we call it X. And this vertical line, it means you can, if you study probability before, that means conditional probability. But here we just say it's given a condition. So the given condition that X, the X have the property P here. So it's very simple. Property P, it can be a large like a large set of property. But some property it may not work. It must be a proposition. So this will lead us to the next situation. So what is a well-defined set? Some sets with the property is not defined. It's not well defined. So here we'll consider that sets, if the set is in the form like X given by PX, then PX is a proposition, which means it can only be true or false, but it must be true or false. It cannot be both true and false, and or like neither true nor false. It must be a proposition. So why this is important, we can see example later. But one interesting thing to see is the example here. So let's first view this example. Let's first view this example. So that set A, B element A, given that A is a left sock. But what is a left sock? Sock, well, it may be like it's right and left sock are the same. So it's undefined, right? You can, because it's not very easily to say which element is belong to this set, which element is not. But if B is defined as B is a sock worn by John Lu, a particular person on his left foot at 2 uh 2:54 p.m. on June 7th, 2024. Then the time is defined. The person is defined, the foot is defined as left foot, then the sock is defined. It must be the only one. Maybe he wear different layers, like 10 layers sock, then there will be 10. But at the least, it is defined. You know which sock belong to this set. But in A, you don't know. You don't know. Possibly you can say, well, there's a lot of sock in my box. I put sock in the box. So but you cannot say which is left. So B is defined, but A is undefined. So A is not a set. Only defined set are called set. So A is not a set. B is a set. A is a statement. So A is a statement. Yeah, it's just a statement. All right. So um, what about this example? The top example is just it's just an example of how to write the set by a property. So x is integer and greater than 0 is equal to y is integer and y greater than 0, because y is just notation. It can change. It's the same, and both of them mean it's like 1, 2, 3, 4 to the infinite sequence of natural numbers. So that's it. And I want to introduce some useful stats in math. Uh, but the definition here is informal. So you don't you just get a sense of what they are. We'll talk about their definition rigorously in probably in the sixth lecture or seventh lecture. Because the definition can be complex. But here is like a basic meaning of them. So natural number n, usually denoted by capital N. It's like 1, 2, 3, 4, 5 to infinite sequence to 100, 1,000, 1 million, 1 billion. and to infinite. And the integer is just like adding 0 to the natural number and also the negative of them. So it's goes from um, negative infinite to positive infinite. Rationals is just a division. It's a rational numbers means it's a division of two integers. So for some a b belongs to z and b cannot be zero if it belongs to zero, while the rational is undefined and x equal to b a divided by b. So it have a lot of probabilities. Maybe you will feel like well, rational numbers are more than natural numbers. That's a intuitive thinking. But probably you'll find out that the number of rational numbers and the number of natural numbers they're the same. They have the same cardinality. And the real numbers, what is real number? Real numbers, because it's informal definition, the formal definition will be very long. We have used 13 axioms to define real numbers, but here it's just like all numbers without I. That's typical. Every number you see without I is a real number. In most of the context. And a complex number denoted by C. Usually some people write a C. I like to write C with a vertical line. So it is in the form of Z equals to X plus IY. And XY is real numbers. All right, so that's and I will use the notation NZQRC later in the course, so it means these things. But the complex number is not occur very frequently for this summer, I think, because it's not going to that deep. Real numbers common to see, and all the first four, all of the first four here, you will see it frequently. All right, and I'll go to the next topic. It's the axiom separation. This is a this is a axiom, or you can say a theorem, maybe an axiom because it's very intuitive to and it makes sure that the given set is defined. So if we already have a set X and a property P, and there must be a set whose elements are in X with property P. So if you ever see a set is in this form or in this form, these two are equal. It's just like a shorter version of the upper one. So X belongs to something given by a property. This is defined. And notice that the property must be a proposition. If this satisfied, then the set is defined. This is because we already have a set here. And the property will just like maybe it's equal and maybe it just like limit the number into smaller numbers later. So there will be yeah, there will be different there'll be a different set. It's smaller, but it's still a set. It still contains the elements in the X, which is already defined. All right. And another interesting fact is about the empty set. I like empty set because empty set is very fun at the beginning. It's written by it's a notation similar to phi, I think, in Greek letters. And this means an empty set, which is here. You can see there's no element inside. It's just a bracket defining the set. Or you can also define in this way, like R here denotes the real numbers. So it's like all of the real numbers which X is not equal to X. Well, which is impossible to have such X. Like if there's one, one must equal to itself. So in this way, we can also define empty set. And it just means a set has no elements. That's its formal definition. All right. And the first, I think we have learned some proving in the last lecture. So there's a theorem which is not very meaningful, but it's a fact. There's exactly one empty set. So let's consider a way like how to prove it, how to prove it's true. Okay, so why there's only one empty set? How do you think about it? Maybe for me, I was first think, well, if I can define another set, which is also have the property of an empty set, and find out they're equal, right? So there's no two different empty sets, so there must be one. All right, that's my thinking. So I write it, write it in this way. So use the contradiction strategy of proving. Suppose there's two empty set, one and two, and want to show one equal to two. So we reach a contradiction. There's no two different empty set. Okay, how to prove it? How to prove one? How to prove the statement one? So we want to show for every element x belongs to um if x belongs to one, the empty set one, then x belongs to empty set two. And if we can prove the if and only if relationship here, then we're done. Then we are done. Okay. And this is because it's the definition of set equivalence we defined before. So let's see what's the set equivalence. The set equivalence said that like x belongs to here, x belongs to A, if and only if x belongs to B. So with the same logic, we'll use this definition here to prove it. So this proves empty set one is equal to empty set two. So because based on the empty set definition, there's no element belongs to one and two, both. So these two statements are always false because there's no x belongs to empty set one. So if both sides of a biconditional proposition is false, both sides are false, then it's true itself because they're in the same truth value, which is from lecture one. All right. So this is proving like two empty sets occur simultaneously is impossible, which means there's only one unique empty set. So we're done. All right. And we're gonna see some examples of empty sets. Like I'll give an example about like a man who run fast. So first set is defined as A. So what is A? A is defined as a human. X is human. Human is a set because, well, maybe in some biological scales aspects that human are not defined, but I think like human are just like what you can observe as a human or non-human. And if X run, so the set A is all the humans who can run 100 meters less than 0.57 seconds. Do you think it's an empty set? Well, I would say it's not a set because this is not a proposition. This is not a proposition. Who can run 100 meters less than 9.57 seconds? Because the word can is not defined. Can means one. Because we know Usain Bolt runs 9.58, which is the world record, but if there's some human beings can run faster, but it's just not record as a world record. So A is not defined, but B is a defined set. Like X is a human that can run, that have run and recorded 100 meters less than 0.5 seconds, 57 seconds. And that is defined. And it's empty because the shortest time is 9.58, which is greater than it. So less than it is impossible. So yeah. So here's an example of an empty set. And we'll see another theorem, which is the empty set is not equal to the set of empty set. So why that? So I think why say empty set is found mainly because of this one. Because we can also get a lot of bracket outside of an empty set and it still be a set. So we're gonna prove it. So we can see. So we can see first like this set, the right side. Okay, we say maybe this set has set one. This is empty set. We say set one contains one element, which is the empty set. It is an element in this set. It's in the bracket. So there exists one element belongs to it. However, empty set has no element at all. So this element belongs to this set. It's not in. It's not in the empty set. So for element empty set, so for element this one, this is false because you can say here this one is true, this one is false. So the biconditional proposition fails to be correct. All right, so yeah, so previous it's different. Cool. And we're gonna see the next page. Uh, so give another example is that, well, what is the set of set of set of set? So this is a clear definition, okay? Let A be set one, because it's long, I want to say it's set one, B is a set of A, C is a set of B. Then we can find out that empty set is in A here, right? So empty set is in A is in B, A belongs to B. This is true, this is true. B belongs to C because B is here, so it's true. But if A belongs to C, there's no A. There's no A here, so A is not belong to C. Although A belongs to B and B belongs to A, but A is not belong to C. We can say this as not transitive, like you cannot transport from one relation to another and to another, right? So it so we can say that, yeah. And empty set is in B. No, there's no empty set here. Fails to be correct. It's but this statement is true. This statement is true. But if you say like it's the empty set belongs to B is not true. I know, but there's one interesting thing. Empty set is definitely not belongs to C, but it is a subset of C. This is a subset notation, which we'll see soon. All right. And all right, that's the basic definitions of set. So probably now you have a like a basic understanding of what a set is and how to deal with it. If that's fine, then you reach the goal. And next one, I'll talk about a fun fact. It's called Russell's paradox. It's like uh its finding is just like, well, um some set um is very hard to define, or some set is not exist if it contains some special element. So we can define set like that. We can define S is a set of A. A is a set and A is not an element of A. Okay, so this is a property. This is a property. This is an element. So it seems like S is defined, right? But what about if we say if is element S belongs to S? Is that correct? And let's say suppose it actually belongs to S. S itself belongs to S. Then what happened? What happens? S is a set, and it must follow the property here. So this one is followed from this one. So S is a set, and S is not belong to S. Correct? And but if this is true, then if and it is a if and only if relationship, then because definition is always if and only if by set definition, and we reach this conclusion. Well, it looks very strange. S is an element of S, but and also at the same time S is not an element of set, which is a paradox. So and the Ross cell is the first mathematician found this one. So it's given by his name Russell's paradox. So this is the paradox occur. They're choose a companion because they are true and false in the same proposition. So the truth of this one will always lead to the falsity of this one, which is a contradiction. All right. So the property PA doesn't define set in one, which is here, which is this is one. Okay. All right, so this doesn't define set. So what conclusion can we see there? Uh, I would say not every property defines set, or a set. There's exists a set that doesn't contain everything because S is not element of set S. and property P, which is defined here, doesn't define set. So yeah, so this is the main result from Russell's paradox. You might feel it's really strange to understand the Russell's paradox logic right now. It's totally understandable because when I study Russell paradox, I spent about 2 weeks to figure it out by looking at many examples on YouTube and on other resources if you like. So you can get a sense of like uh what's Russell's paradox. So the two main results from Russell's paradox is uh there's nothing there's something not belong to S. The S itself, we already see it here. And also there's no set that contains everything because S is not in S is not in it. So the color is very direct from Russell paradox, which we deduced here. Okay. All right. So we'll see some solutions to avoid Russell paradox. Remember, Russell paradox is defined here, which is it defines A without saying like A is belongs to some set. But remember we have a axiom before. It's called axiom of separation. So this form always defines that. What's the difference between them? It's like it defines the element is belong to some original set X. So if we can if we can define some original set that A belongs to, then property P, if we follow the same property P, then it must be defined because S like for example we go up to see it. If we say like A is belong to some set X, then what's the difference? So there must be two situations. S is in X or S is not in X, right? If it's X in X, so first let's say if X is not in X, then S is not in the domain of consideration. But if S is in the set X, if it's inside it, then well um S is not belongs to A. S is not belongs to S. Then this condition say S is not belongs to S. So it mainly says it is not belongs to it because the set S is contained in X. And if in this case like S is in it, then there is nothing S that must not be in the X. So this is a solution for solving Russell's paradox just by setting a original set that X belongs to. Um, okay, okay, and the next several examples is about quantifiers, which is like logical operators too. Like there exists for all, something like that. But we'll first define what's a variable. So probably you already know, like in some equations, if there's an x which is undefined, it can take many different values. Then it's a variable. So for example, we can easily see if x is equal to 1, then and then like this statement, this statement here becomes a true proposition. And x equal to 4, then 2 plus 1 equals 3, not 2, which is a false proposition. But x can be replaced by different values, then x is a variable. And there might be many values, infinitely many values for x to be chosen from. Or x is limited in a very small domain, like there's only two values, 1 and 2, for x to choose from. So that's a variable. At least it has two different values to choose from, then it is a variable. So this leads us to consider some quantifiers. So the first thing, the first quantifier is uh, is called existential quantifier. This one. So It means like there exists an variable x such that the p is true if written this way. This means this read as this, and it means the given statement p is true for at least one substitution of the element x in p. So there exists at least one or maybe more x that can satisfy p, and x is an element of p. For example, p can be written as 1 plus x equal to 0. Then there exists an element 1 that make it true, right? No, -1 make it true. Okay, so this is the existential quantifier. And the second one is called the universal quantifier, which means for all x such that p is true. So p, something with x, is true for all x. For example, I can give an example of this one. Consider like x times 0 equal to 0. Then this is for all x in real numbers, because everything times 0 is 0. So this is true for all x. We can say for all x, this is true. All right. Okay. And there's one important property of this one is that for all xp is logically equivalent to it is not the case that there exists x, it is not p. So how do you understand this? Let's say um there exists x not p, which means um so which means like the p is not satisfied for at least one x. And it's if not the case, then it's like for all x, the p is satisfied, which is for x, p is satisfied. So this is how we understand it. And uh, and I think it is somehow intuitive. Uh, and you can treat it as a axiom. Not case, because consider if you need further explanation, like um there's like 1, 2, 3, 4, and the set has 4 numbers, and you need to see if 0 times this one equal to 0, then you can say there exists x. It's not make this not true. Is it possible? You can say, well, it's not possible because all of them x times 0 is 0, which is this one. So it is not a case there exists x in these 4 numbers that makes this false. So I think I think this is a clear explanation of what you think before. Okay. And one important abbreviation is such that writing ST. Maybe this is the first abbreviation you see in math, and it's very common if you see it many times before, many times later. And I remember the most crazy one is this abbreviation. It's called W, let's say LOG. Anyone know what this is? This is actually without loss of generosity, which is talk a lot about in stochastic process. Without loss of generosity, then what happened? It's really like we can consider only one case instead of 10 cases, but the generosity doesn't lose. It means that there's many fun abbreviations in math, and such that is the beginning of the level of abbreviation. So after introducing existential quantifier and universal quantifier, there's also 2 more. But this is easy to understand. So means there exists only one unique x that's satisfied. If there exists 2, then it false. So there's usually a proving strategy of this one. It's like you can first show the existence. Like you just show here, there exists one x satisfied, and then shows if there's then to prove its uniqueness is that P is true for if it's P is true for both x1, x2, then x1 is equal to x2. So that's like you can prove its uniqueness, just like what we prove for the uniqueness of empty set, right? And this one is interesting. So it means like there exists no x such that P is true. So how do you understand this? Which means like you cannot find x, uh, you cannot find any x that satisfy P. For example, let's say, well, we can give example of this one. Like let's say, x there's only x can be only choose from 1, 2, 3, 4. So there x is choosing from this domain. And the proposition is 1 times x equal to 0, then you cannot find 1, right? So that's what this simple symbol means. Okay. And and from the last example, we can see if you said x can be chosen from any real numbers, then this is false because you can choose 0 times 1 equal to 0, but we define x as limited inside the four elements. So the truth value of a quantifier's proposition, which is the quantifier proposition, is like in the form of this four, the four here, depends on the set from which the elements come from. And such a set is called universal set or domain of interpretation. All right. So it's very important. You can define it as four numbers. You can define it as a natural number, real number, complex number, or like or maybe like a more complex one, like all the rational numbers smaller or equal to 100, something like that. But if the universal set changes, then the result also changes. So let's see one example. So there exists x smaller than 0 is true when the universal set is all real numbers because you can find -1. So -1 satisfies okay. But it's false if the domain of interpretation is all positive numbers. So it's impossible to find because -1 now is not in the domain of interpretation because -1 is not positive. But in the set of all positive numbers, there's no x. There's no x which is smaller than 0. So this is the importance of choosing a like descriptive universal set for quantifiers. There's two interesting propositions of quantifiers. One is like there exists x. It is not case of there exists x. P is like for all x not P. This is intuitive. For example, you say there's no x satisfy P, right? The formal one means that one. There's no x satisfy P, which means for all x, x is not satisfy P. So these two equivalent. And also like it is not the case for all x satisfy P, then there must exist one x such as satisfy not P. Then or you can say if for all x satisfy P, then uh there then like so it is not the case that all x satisfy P. So there exists x among all the x that satisfy not P. This is equivalent. And there's some and I think the next theorem is really important. It shows the order of quantifiers matters and can lead to different results. So first, let's consider the universal set as R. And for all x1, there exists x2, x greater than x1 greater than x2. Is this true? Well, let's think about it. So for x, like you can say x is very large, it's a large one. But because the real number is unlimited, there exists one x belongs to real number, uh which is greater than like which is smaller than x1 here. If yeah, if you pick x1 for x1, very, very small one, goes to negative infinity. Like this is the real axis. We choose this is 0. If you choose x1 here, then we can always, because this is unlimited, we can always choose x2, and x2 is smaller than x1. So this is true, right? But consider a different way. Consider here, um, for all x1. So there exists x2 for all x1. X1 is greater than x2. Is this true? Let's think about it. So same real line, and this is this is 0, and there exists an x2. For example, we pick x2 as small as possible for such that for all x1, x1 is greater than 2. For this set x1, this is non-limited, so it goes like open. So this portion x1 is greater than x2, but we can also extend this line to infinite long. And for this set, x1 is smaller than x2, so such x2 doesn't exist, so which is false. So you can see what's the difference between these two is just like we change, we just change the order. We just change the order of these two and makes different result. So these two are not equivalent. It's not logically equivalent. Cool. And there's some examples you can see. Yeah, let's talk about one of them. So for all x, there only exists one y, xy equal to 0. Mm, is this true or false? I think it's false because there exists x equal to 0. So proving something false, prove some for all statement false is to find a contrary example. So x equal to 0 is a counterexample. So 0 times 1 equal to 0, 0 times 2 equal to 0. So y can be two different values. It's not unique. So the statement is false. And for 2 and 3, I write it out and with the reasons so you can check later. Um, but we also, but 3 I don't write the reasoning, so I will talk about 3. So x greater than or equal to 0, which means there if this, so we are analyzing this way. So we will show that if this is t, then this must be t. Okay, so x greater than equal to 0. So if 0, then x is in this part, including the 0. There exists y, such as y squared equal to x. Yes, it's correct because if x is greater than 0, then for example, there's some x, and we can find y. For example, if this is 1, then y equal to 1. If this is 10, then y equal to root square 10. But we can also find the y, such as y squared to x. So this is a true one. All right, so the next topic, I'll talk about subset, which is I already mentioned before. This symbol is a subset. Subset is easy to understand in a way like it's just a set that is smaller than another set, but contains all of the elements inside the set. So, which is to say, if you say A is a subset of B, then for all element X, uh, if X belong to set A, then belongs to set B. And other ways to say it, like B includes A, B contains A is contained in B, and this symbol is called inclusion symbol. If you want to say like A is not a subset of B, we just write, well, we just write a line above it. We just write a line above. So A is not belong to set B. Or it is not the case that A belongs to B, something like that. And I'll give two examples. The set of empty set is belong to not belong to is a subset of set of empty set because um four element empty set you can find is here. So which is the same here, which is same here says like for x belong to this one is belong to this one, for which we can prove it. And another example is from the definition before. Natural numbers belongs to integers, belongs to rational numbers, belongs to not a subset of real numbers and subset of complex number. This is the set inclusion of different uh very famous set of numbers in math. All right, and the proof strategy for negative set inclusion is to prove as like if A is not a subset of B, then it's not the case that for x belong to A leads to x belong to B. So there exists the x used the quantifier proposition. Not the case for A, then it's like there exists x not subject not this one, or there exists one x. X belongs to A and X not belong to B. So this is what we will use very frequently later to prove some set is not included in another set. Cool. And there's also some new theorem later. So the first one is if A is a set, is for all set A, we can say that then A belongs to A is a subset of itself, and also empty set is a subset of A. So to prove it, well, let's prove the first part. A is included in the self. So for x belongs to A, it leads to x belong to A. They're the same, so there must be T and T. So it's true from the conditional proposition. And the second one is like for x belong to empty set leads to x belong to A. Well, x belongs to empty set is always false. It's always false because there's no element in it. But conditional proposition becomes like f leads to some t or f, but f leads to t or f leads to f is always true. So this is also this is always like the topology, or it's a correct theory. And the next theorem is if A is a subset of B, B is a subset of C, then A is a subset of C. This is the transitivity of the set inclusion. And you can read the proof later, but I want to give a diagram of it. X in set A, then it's in B. All of the X in A leads to X in B, and all of the X in B leads to X in C. So basically the thinking process is to find 4x in A, then it's in C, then it's the inclusion. So we're done. So that's the logic here. And there's also something called a set equivalent theory. You want to prove A equal to B. Before we prove like 4x x x belongs to A if and only if x belongs to B. But now if we have the set inclusion defined, we can find a different way to define it, different way to define the set equivalence, which is if you can prove A is a subset of B and B is a subset of A, then A is equal to set B. All right. And the proof strategy, you can read it later. You can read it later. But I will not talk about today. The the basic logic is to use the definition of set set equivalence from the beginning, like what I said before. X belong to A if and only if X belong to B. Yeah, and you can solve it from two different let me say directions. First, suppose this one is true and lead to this one. And suppose this one's true and lead to this one. So you prove the if and only relationship. All right, so let's talk about the next definition, the proper set, the proper subset. So if you can see that there's a different notation which is don't include the horizontal line at the bottom, then it's a proper set, which means it is not only like A is a subset of B, but there exists a X belongs to B and X not belong to A, which means like you can think about A is strictly smaller than B, and all of the elements in A is in element B. So there must exist one X belongs to B that is not in A. Okay, and let's see some example. Let's see some example. If the two sets are equal, then it's not. If A is a non-empty set, then empty set must be a proper subset of A because there must be exist one element in A, any element, but it's not in empty set. And this example is interesting. 1, 2 is a proper subset of this set because you can find element 1 and 2 here, and there's an element not in this one. But this is also belongs to the set because the element is here. The element is here. So the set 1, 2 is both you can write three different things. 1, 2 set is a proper subset of this one, or is a subset of this one because proper subset is always a subset because subset definition is more general. And also you can say 1, 2 is an element of it. All right. Is empty set a subset of all set? Uh, empty set a subset. Yeah, it is. It is definitely. But it is not. Yeah, empty set is a subset of all set, but empty set is not a subset. It's not a proper subset of all set because there's only one exception. Like empty set is not a subset of itself, a proper subset of itself. Is that answer your question? You can open your mic, say about it. Yeah. All right, sounds good. Yeah, thank you. And sure. So yeah, so we have done. I know. Yeah, today's time is very limited, so I'll talk about set operations. I'll quickly talk about it because I think it's you must understand it. Set difference A minus B or A this symbol B, which means like X is in A but X is not in B. All right, maybe I will use this Venn diagram to show it. So set A, set B, they're together, and A minus B, which is this part, the part that is belong to A but not B. And in this one is intersection, which means it's both in A and B, which is the center part. And if you say union is like at least one set contains, then it's this one. And usually we can denote a universal set, as we said before. You can remember the same definition as universal set, the set, the domain of interpretation. That is below, it denotes by this large square. And this one is called complement of A. Complement of A is all of the elements inside the universal set, but it's not in A. And there's one found definition called disjoint. A disjoint from B, then what does it mean? It means that there's no common elements between A and B. You can see here, there exists a tangent line that separates A and B out without touching it. Or yeah, without touching both A and B, then and it is destroyed. And there's some, and I think there's also one different definition called pairwisely destroying. What is that? It's like there's many different set, and for each of the two, if they make a pair, they're destroyed, and all of the combination of all of sets are destroyed. That's for set more more equal to three. If there are if there's three or more sets, we can say pairwise destroyed, because destroying of three sets might look like this one. It might look like this one, or maybe four. So this is a disjoint set of four, but it's not pairwisely destroyed, because you cannot find a common element that belongs to all of the four sets, but for each of two, you can always find a common one. So it's not pairwise desjoint. Okay. And there's some theorems. There are some theorems which is associative laws, distributive laws, De Morgan's laws, very similar to the logical operators definition too. It's just like changing the notion of and to intersection and or to union, and all of them is the same. And just to change the not maybe this one to complement, so you get a De Morgan's law. And there's one different. The only one difference is here. Okay, let's see if I can make it clear here. So this is the only difference. This is not in the logical operators. It can be true. I have not checked before yet, but it is true in the in the De Morgan's laws considering sets. It's like the difference between A and union with B and C is equal to A A difference between A and B intersection with A with C. And if we change the union to intersection, then it also makes sense. So yeah, so that's it. And we can also prove, let's say we can prove, yeah, I can leave as an exercise for you to consider how to prove all of them. Associative law is very easy. Distributive laws might be a little bit difficult, and the proof of De Morgan's laws may be maybe even harder. But I will give one example of proving this one, proving this one. So let's see what's the strategy that's commonly used. So to prove two sets, this is a set, right? This is also a set. So prove two sets are equal. Then we want to show four x belong to one set. Um, the x is also in the different set. In the uh, for x in this one, x is also in this one. It's a if and only if relationship. So let's consider this one first. So this means x not belong to A union with B. And if x is not belongs to A union B, then x not belong to A and x not belong to B. So this is use the De Morgan's law for logic operators here. So x not belong to A union with B, so x does not belong to the set. This is defined by the union set, like x belong to A or x belong to B, which is to say not the case x belong to A or x belong to B. So x belong to A and x not belong to A, which is the false companion. X not belong to B is also a false companion, and intersection with them is the De Morgan's laws for operators is used in this step, and this leads to this one. Okay, so which implies x not in A, so X is in the complement of it, and X in the complement of B, which is the same as this one by intersection, set intersections definition. So we are talking about this one. So probably, yeah, probably I will leave the index set to next lecture because it's already 10 o'clock. So yeah, the next lecture I'll talk about index set and also um, another important uh, type of set called a power set and sigma algebra. What's the difference between it and power set? And set partitions. Maybe that's it. Maybe that's it. That's for the next one. So does anyone have any questions here? You can open the mic and ask. Okay, so yeah, so maybe that's all. And see you 2 days later.